follow up on Yuri's talk, where the focus will be more on the exterior of a magnetar and the electromagnetic fireworks that are associated with them. But as you'll see, a close connection develops with, for example, understanding the plasma state outside a magnetar and understanding its crustal physics. So these sources, of course, are defined by the fact that they are powered mainly by the decay of very strong magnetic fields, 10 to the 15 to 10 to the 16 Gauss. And one way to phrase this is that the time averaged rate of release of energy, either in more gradual X-ray emission or in really bright outbursts, averaged over time, can easily reach 1,000 times the rate of release of spin energy by electromagnetic torques. So one feature that's emerged over the last couple of decades and got increasing attention is that the currents flowing outside the stars, in strong contradiction with radio pulsars, can approach in strength those flowing in the interior and supporting the magnetic field. So that poses some significant challenges in understanding the QED processes that support the currents. It leads to the possibility of a matter state, in effect, which is electromagnetically dominated, in which electron-positron pair creation maintains something close to ideal magnetohydrodynamics over a wide range of scales. But at the same time, in more quiescent states especially, there's a possibility of a direct imprint of QED processes in super-Schwinger magnetic fields in, say, the persistent X-ray spectrum. And in a way that involves, qualitative changes in even the processes that might be mediating, spectral formation in an accreting 10 to 12 Gauss neutron star. So a central puzzle, hardly the only one, is that magnetars produce bright electromagnetic outbursts, and those are, of course, first discovered in the X-ray band, but they also rather rarely produce very bright radio pulses. And understanding why that radio emission is relatively rare is a central part of our research. So I should first list the names involved in the research I'm going to describe. You'll notice how young they all are. And there's one name that appears twice, Kushik Chatterjee, who's moved between Maryland and CETA. And so this group of people has worked substantially on the magnetar exterior, all the physics I've just described, but also in many cases on the interior as well. So one great advantage of studying these rather exotic objects is, in contrast with gamma ray bursts, in contrast with core collapse supernovae, which of course have long been of interest to high-energy astrophysicists, you can see in nearby magnetars the physical processes building up that lead to a bright outburst. And you can study them across the electromagnetic spectrum, producing bizarre behavior by the standard, say, of radio pulsars as previously studied over decades. This includes bizarre, radio pulse behavior. It includes unusual X-ray spectra, and through painstaking work, especially of Vicky Caspi's group and Chris Okulutu's group, we've been able to monitor their spin down and their burst behavior over decades. And one observes, remarkably, a huge range of timescales in these objects, from sub-millisecond onset of ultraluminous X-ray bursts or fast radio bursts to very slow deformations lasting for weeks to months to years even. So there are two broad approaches to understanding that huge range of variability. One, of course, is to study instabilities of the electric current outside the star along the domain of solar physicists, but here extrapolated in quite different electrodynamic regimes. The other is to study the stress evolution in the outer crust of the neutron star, and Yuri gave a beautiful overview of that, which is hugely stress and temperature dependent. There are huge nonlinearities in the response of the crust to applied magnetic stress. And then very strong nonlinear feedback of the deforming crust on the magnetic field itself, and importantly on the external currents, and therefore on, say, QED processes operating outside the star. So there really is this very tight synergy between the interior physics and the exterior physics, and the two can absolutely not be separated from each other. So another way, say, to rephrase this is that you twist up the magnetic field, then electrons at 20 to 30 times the radius of the star see thermal KV photons at the cyclotron resonance, and there's a very strong redistribution. The optical depth to scattering at this resonance is basically dependent on the twist angle of the magnetic field. So you have an enhanced resistivity. You can think about the resistive evolution of this circuit. And then at the same time, if you're interested in the outburst behavior, your interest is, of course, understanding the instability of a current, both outside and inside the star. And there is a very direct imprint of crustal physics in something as simple as the duration distribution of the very bright repeating X-ray bursts that are the initial hallmark of the soft gamma repeaters. You know, over decades of burst energy, the burst duration tends to cluster around 1/10 of a second. What's 1/10 of a second? Basically the time for an elastic wave to move around the neutron star, and for stresses to re-equilibrate in response to some shift in the magnetic field. So interestingly, this also applies to the very bright, ultraluminous part of the giant flares, the one part that is detectable to megaparsec distance and generally can be thought of as a third type of classical gamma ray burst. But as I said, in contrast with the binary merger or collapsar type gamma ray bursts, you have a much finer grained possibility of studying the structure of the magnetic field and details of the source right up to the point of outburst. So T is the time, yeah. To the left you see the duration, 10 to the minus 1 seconds typically, okay? So then let me quickly summarize some of our accomplishments. How do you energize the magnetosphere at a high enough rate to produce one of these ultraluminous bursts, right? So there are two basic possibilities. You twist or you shake. Twisting, of course, has a long pedigree in solar flares. Here, the Maryland group has pioneered the first magnetohydrodynamical studies of the transition from quasi-static evolution of the currents to a dynamic high Lorentz factor escaping electromagnetic pulse. Okay, so there's some commonality, of course, with coronal mass ejections, but a substantial additional numerical challenges in accommodating the high magnetization. So you switch in some parts of the computation between force-free and magnetohydrodynamical descriptions, for example. And then Ashley Bransgrove, and the student, has greatly improved our understanding of how a localized release of elastic energy in the crust would actually dissipate. How much goes into the core, how much comes out, in what form does it come out? And that is, to my mind, the first fully self-consistent model of the dissipation of quake energy in a magnetar. So then, as regards the external electromagnetic field, there is the interesting question of if you suddenly shake the magnetic field or compress it, what is its nonlinear behavior? There's an interesting point made by Andrei Belvorodov a few years ago that steepening compressive waves can genuinely steepen into shocks. And Michael Green PhD student in Toronto, has some beautiful new simulations describing some subtleties of that nonlinear behavior. Then, maybe I shouldn't go in quite as much detail here, but there's the first self-consistent study of how current dissipation outside a magnetar could produce kinetic scale turbulence that would plausibly convert to radio waves. That's also led by the Maryland group. A student, the T in there is not an initial, it's the advisor of mine, and I have extended previous work on QED processes outside magnetars to consider what is actually the global self-consistent state of plasma around a magnetar. Is essentially the plasma really collisionless, as long experience with radio pulsars, which suggests that it should be, and for which there is already a well-defined and succinct model. Then when you understand the plasma state, or at least understand the possible variations of the plasma state, and therefore of the E dot B distribution around the neutron star, you can consider the implications for axion emission. Ani Prabhu, postdoc and a PhD student he was working with, and I looked at that. And then finally we have some more recent work that's close to completion on small-scale current structure around magnetars. Okay, so I'll discuss in a little bit more detail the possibilities of twisting versus shaking. And then regarding the electromagnetic pulse development, I guess the most succinct question is, when you have a nonlinearity developing in the magnetosphere with a huge ratio of magnetic energy density to particle energy density, is the effect of magnetization that you should apply to understanding the shock physics really that high, or can small irregularities in the magnetosphere effectively change the magnetization? This is an issue that has come up previously, for example, in gamma ray burst outflows, where the electron magnetization could be enormous, and the effect of magnetization much less so. So Kaushik Chatterjee has produced the first quantitative model of a giant flare that can really be meaningfully cross-compared with data. So let me just say a few more words about what is known about the giant flares of magnetars. So they can dissipate as much energy, apparently, as is stored in the external dipole magnetic field. Okay, and they have this. They show some strong variability at the beginning. There are a handful, at least, detected outside the Milky Way. You can resolve the initial spike much better in such extragalactic sources. And you, oops, I need this thing. You see some variability over tens of milliseconds, over about 10 milliseconds, but then over maybe 100 milliseconds, the source can release even more energy. So there are distinct timescales, one perhaps associated with fast current relaxation in the magnetosphere, and the second with a gradual response of the solid outer layers of the star. So Kaushik wisely has chosen the simplest configuration of a dipole field and then twisted it, and then you see, as in solar flares, you see an opening out of the magnetic field and reconnection forming, and the closing back of the magnetic field and with reduction of the twist. But at the same time, one is able to track the formation of a fireball, and one is able to reliably calculate for the first time in a magnetar giant flare model the proportion of energy that's escaping directly as a low-frequency electromagnetic pulse, the part that's directly escaping and as an positron fireball, the portion of the fireball energy that remains trapped. One of the arguments for strong magnetic fields in magnetars comes from the observation of trapped fireballs in the giant flares. And then the characteristic timescales associated with the relaxation of the magnetic field. So, how does one set this up? Well, just one quick comment, and that is that this is where the solid physics comes back in, and where our understanding is still is quite incomplete. The the effective thickness of the magnetar crust is quite small, maybe a few % of the radius of the star, if you weight the thickness by the shear modulus, which is very strongly dependent on depth, okay? And so then thin elastic shell, you apply globally stresses to it, say as the magnetic field in the core comes into imbalance, naturally produces localized concentrations of stress and leads to the formation of fault-like features. And it's a question about how mathematically fault-like they really are. So that's a natural starting point, which is how Kushik set up his simulation, which was to apply a band of differential rotation at some latitude in the magnetar, and then let the magnetic fields outside initially respond quasi-statically. So the initial response is force-free, but then the relativistic magnetohydrodynamics kicks in once you start creating plasma and you start dissipating. So here is, how does this work? Here is the time evolution. So you see in the top, the toroidal magnetic field developing. You see an expanding view. You see there's dissipation going on here. Yes, this is a fireball forming. But at the same time, if you zoom in near the closed magnetosphere, the plasmoids are coming in, the magnetic field is reconnecting, and you're building up hot plasma in this confined zone. And the right proportions, more or less, as are needed to explain the brightest magnetar galactic flare ever detected in 2004. At the same time, in commonality with Carrington events, extreme CMEs, you see a very strong angle dependence of the energy flux. And so there's an interesting question that the authors raise about the possibility of orphan giant, I guess, orphan oscillating tails, where you don't see the initial spike. Okay, there it goes again. I'll let you see it one more time. So there's ongoing work generalizing this to higher multiples, which could lead to some interesting changes in some features, but not all. Okay, so then Yuri already covered the nice work out of the Columbia group developing a new model of magnetar flares that involves magnetic buoyancy. And yes, Ashley's at, yes. My apologies. And so, just some context, the brightest gamma ray flare of a magnetar also produced the brightest radio afterglow, which has been fairly convincingly connected with the ejection of maybe 10 to the 24 to 10 to the 25 grams of matter from the magnetar during the burst. One possibility is that you have a magnetic flux tube escaping suddenly across the surface, carrying that matter with it. The pair fireball by itself isn't enough. It's relativistic plasma. It doesn't have enough inertia. So one does want to have competing theories to contrast against each other when considering something like this. And so I will draw people's attention to a simple idea for explaining some of the bright afterglow that's detected from the surface of magnetars following bursts of large to intermediate energy. And so this basically involved the idea that, well, you twist the exterior magnetic field, you dissipate the current, there's volumetric heating. At the same time, the magnetization of the outer parts of the neutron star is quite high, the ratio of magnetic to internal energy density. And as a result, you will not just heat the exterior, you will also heat the outer layers, but in a way such that heating is inversely dependent on density, because the density drops rapidly outward. And so if that process happens multiple times, then you keep on levitating that heated layer because it doesn't have time to cool during the first 10 to 100 milliseconds. And with about half dozen to a dozen repetitions, you eject it. So this does motivate studying magnetar giant flares with slightly more complicated topologies. The twisted dipole wouldn't do this. Okay, now then, once we scale back a bit from the brightest gamma ray flares, we are still left with some remarkable phenomena. Magnetars can go into some states where they produce lots of X-ray bursts fairly quickly over an extended period of time with a total energy that might be not much less than a giant flare, right? And it was indeed during one of these episodes that the galactic magnetar SGR 1935, blah, 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 produced a couple of very bright radio bursts that genuinely deserve to be called fast radio bursts. And so then we have a situation where we don't know the details of the magnetic field in that particular event at that particular time, but we have some strong constraints on when the magnetic field was deforming and at what rate. And so one well-defined approach to this problem is to consider the possibility that some proportion of the energy that might be deposited in twist is converted to a compressive wave. Now, this is a very natural process that has been pioneered at a computational level by the People Move Institutes, but by Yaji Wan, Alex Chen, and other colleagues at Washington University. The collision of two Alfvén waves in the magnetosphere, which is the setup in this middle panel here, naturally, if the Alfvén waves have a large amplitude, creates a compressive wave where they collide, okay? And that compressive wave then can move radially outward. And Andrei Belobrov produced a very impressive analytical treatment based on method of characteristics of caustic formation when the wave becomes nonlinear that can be tested against computations. At the same time, a fully ab initio numerical simulation with relative static MHD allows one to consider much more, not just more complicated, but more general initial conditions. When the Alfvén waves are excited, for example, you expect waves to be excited out in the part where the fast compressive wave might be breaking. And so Michael Green has just put out a paper submitted to APJ discussing how, for example, for pre-existing wrinkles of sufficiently large amplitude, the wavefront can break up, you can produce multiple shocks, and then the effective magnetization of the magnetosphere can drop because the first forward shock might actually then leave only limited magnetization for the next primary monster shock. Then the next question is, what role does direct compressive wave emission from the neutron star play? Again, there is this first fully complete simulation of elastic wave evolution, including both the coupling to the core and the exterior, that lets us for the first time really calibrate that. And let me just focus on one implication of all this physics for fast radio bursts. So one of the primary places one might consider fast radio emission to occur, burst emission to occur near a magnetar would be in the current sheet outside the co-rotating magnetosphere, outside the quote-unquote Y point, this the Y point structure in the external magnetic field. And so one thinks that, for example, the giant pulses of high voltage pulsars are probably emitted by this structure in the form of dynamic magnetic islands that couple to compressive waves, to fast waves that escape as, say, gigahertz waves. So then one model suggested by Yuri Lubarsky a few years ago is that, well, you set out a compressive wave and it squishes this current sheet and therefore increases the amount of magnetic flux that reconnects and increases the energy in the magnetic islands and in the higher frequency waves that are emitted from it. Another possibility that's connected with Chatterjee's work is that, well, you actually change the connectivity. For the same energy, you change the connectivity, sorry, not the connectivity, the well, you do change the conductivity of the external magnetic field. The boundary of the co-rotating, the boundary of the closed magnetosphere. All this would be happening well inside the speed of light cylinders defined by rotation. And then as you twist up the magnetic field, it relaxes back by reconnection. And so, in fact, for the same energy, you do get more energy out by that second process, a point that Maxim Lutikov has made in his work as well. So the point here I'd like you to take away is that our understanding of the energization of the magnetosphere is becoming concrete enough that we really can begin to distinguish between models based on, say, even simple energetic considerations. Okay, now what about the persistent radio emission of magnetars? So this has a couple of unusual aspects. Most of the time, they don't produce radio pulses for reasons we don't fully understand, probably associated, I think, with the non-local pair creation, but that's one opinion. So when they are active as radio pulsars, they are unusually bright at high frequencies. They're the brightest pulsars when they're seen at 100 gigahertz in the sky. Okay? So they have inverted spectra, very unusual, or can develop inverted spectra, very unusual by the standards of radio pulsars. And they also show a lot of microstructure that the individual radio pulses might show the type of polarization swing that's characteristic of an ordinary radio pulsar, but then it breaks up into lots of very narrow spikes. So a first question then is, where does the very high frequencies come from? How does one understand that? Well, if you twist the magnetic field, as the Maryland group has noted, you increase the plasma density significantly. And they've started with the simplest configuration, where you have a thermally emitting magnetar. And the point here is that at X-ray luminosity of 10 to the 34 to 10 to the 35 ergs per second, there's great resistance of an electron or positron moving across the X-ray photon flux at a radius where it sees the keV photons from the surface at its cyclotron resonance. Okay? And so the positrons shown here tend to move with high Lorentz factor with the photon flux, because the photon flux becomes self-collimating, more radially directed as it flows outward. Okay? And so that then motivates the following idea that it was initially pointed out by Andrei Belorodov, that if you have this strong resistivity applied to this circuit, you have this strong background this background twist, this strong self-inductance of the circuit that forces the current to be present, then the electrons and positrons are forced to move differentially, and as a result, you can expect to build up a two-stream instability, and that is not self-quenching due to the high self-inductance of the circuit. So here are some results showing the fluctuations in plasma density and the development of a longitudinal and transverse electromagnetic modes in response to this enforced kinetic instability. So this is a very interesting approach to understanding the high frequency emission, because the plasma densities in the closed magnetosphere can be high enough to explain emission around a gigahertz. Okay. So then let me just quickly summarize some work on the kinetics of the pair plasma, well, especially on how it's produced, because this connects back up at the end with the crustal physics. So the magnetars in quiescence, as I said, are incredibly bright in X-rays. And in fact, most of them, because they don't produce bright outbursts, were initially cataloged as accreting X-ray pulses. They have some 1 to 10 keV emission. And then people looked at high frequencies and found remarkably that the spectrum actually starts rising again. The energy spectrum starts rising again above 5 to 10 keV. And in many sources, not the brightest necessarily and the ones that are most likely to be optically thick to scattering around them, but in many cases, this looks a lot like Bremsstrahlung. So Bremsstrahlung, is a process that in astrophysics is thought to involve electron-ion collisions, and well, you can get something like this out of the surface layers, but it doesn't quite work. Then a student and I realized when we just worked through some basic QED, very basic QED, but in super-Schwinger magnetic fields, that in fact you get this spectrum just from the simple annihilation of cold electrons and positrons. At ordinary pulsar magnetic field strength, 10 to 12 Gauss, the line is somewhat broadened, but it is still a line. But above 10 to 14 Gauss, it flattens dramatically. And most of the energy comes out in one photon and the second in a soft photon. In fact, the two-photon decay is strictly a soft photon correction to the single photon decay, which is mediated by the background magnetic field. So the implication of this emission model is that you have a lot of emission around one MeV. The magnetosphere is being bathed with MeV photons. And then furthermore, those MeV photons have an enhanced cross-section for colliding with each other. It's basically a result of kinetic equilibrium, that the phase space density of particles in the strong magnetic field is enhanced, of the charged particles is enhanced compared with photons. And so the cross-section to go into photons, to go into pairs is enhanced compared with the cross-section to go back into photons. And so you can just start with some very simplified current configurations and then study how the non-local electron-positron pair creation would change the electron-positron dynamics in the sense that you may have zones with enhanced current density, but like in the solar atmosphere, you also have more broadly distributed currents. And especially, it's the currents near the poles that would be responsible most likely for radio emission or for changes in spin-down torque. So if you can supply the current by simply creating trans-relativistic electrons and positrons, polarizable gas of electrons and positrons in this non-local way, you dramatically change the voltage that's excited in large parts of the magnetosphere. So, for example, the mechanism I just described for kinetic instability, for emission of quasi-longitudinal, quasi-transverse modes around the plasma frequency would likely be quenched in the presence of this non-local flux of MeV photons. So we have the beginnings here of an ab initio approach to understanding when a magnetar would be a radio source and when it might not be. Okay, at the same time, there's great interest in the axion community in magnetars as sources of axions or as sites for the conversion of axions to photons. And the particular study led by Sikh's postdoc Ani Prabhu, a PhD student working with him, involved considering just a magnetar near the galactic center where the density of dark matter axions, if the dark matter is axions in the relevant mass range, would be expected to be highest. We know of one magnetar, at least, that's quite close to Sagittarius A star. And so here, one can contrast the predictions of two different circuit models, the collisional circuit model I just described, and a collisionless circuit model involving counterstreaming electrons and positrons in a more double layer type structure with more smoothly distributed currents. And then ask, well, if axions are just falling in and then seeing a plasma resonance close to their mass, and then resonantly converting to photons with a narrow spectral distribution, how bright could it be, and could you set limits on the axion mass and electromagnetic coupling that way? And the answer is maybe under somewhat ideal conditions you could. Okay, then let me finally close with some recent work that has been done in Toronto, but inspired very much by the collaboration between Bart and by Lorenzo Cerrone at Columbia and his group on the nonlinear evolution of small-scale currents in magnetar magnetospheres. So this has multiple possible motivations. One is very simply, as we've heard, including the beautiful ab initio calculations of Hall drift by Peter Rao that described this morning, that the magnetic field in the magnetar crust can naturally develop very small-scale structure. Now, Hall drift redistributes magnetic energy, but it doesn't increase the energy on small scales. But it does create very small-scale currents. And so these then would be relaxing in the magnetar magnetosphere. And there's a very simple problem, but one which we've considered both in the context of very high Lundquist number, very low resistivity, ideal magnetohydrodynamics, and another with a modified form of resistivity, which one takes into account the formation of zones that are effectively charge-starved, where the current density is too high to be supported by the available charges, and then asked what happens to a very slender flux tube, one that's so slender that even though it might be formally kink unstable, it doesn't know it yet, and it tends to reconnect first. And so with a very simple reversing magnetic field, you can study the distribution of zones of very high current density and their time evolution. And these are promising sites, for example, if this process were to be happening outside of magnetar. These are promising sites for particle energization, and then we're not making any bets about radio emission, but for secondary electromagnetic instabilities as well. So I think then I have come to the end faster than I expected. So there will be plenty of time for questions if anyone has any. But let me just indicate some future directions that are of interest. So I've already described how there is this synergy between the interior physics and the exterior QED processes that are most relevant for sustaining paraplasma outside of magnetar. And these are still disjoint investigations, but they really do need to be brought together in a more convincing way if we are to have a real first principles description of a magnetar, say, at plasma state at the onset of fast radio burst emission. We don't know what the actual plasma distribution around it is if we want to understand its radio properties. Roger indicated that we should all mention one thing we're especially hooked on. Well, magnetars, as they age, may well, they are observed to, it seems, turn off largely as sources of X-ray bursts, bright X-ray emission. Currents in their outer solid crust decay. The external magnetic field may become essentially potential. The magnetic field may be essentially locked into the superconducting core. And then they would sit as inert magnets floating through the galaxy and not doing much. But what happens if they reside in a star cluster? Well, over a period of a gigayear, this 10 to the 15 Gauss magnet could very well collide with another star. And the point is that in contrast with an ordinary radio pulsar, an ordinary X-ray pulsar, where the cumulative accretion energy is easily enough to make a 10 to 15 Gauss magnetic field, but from which you never see magnetar X-ray bursts. Here, the response of the magnetic field to accretion is substantially delayed, okay? If you want to build up enough mass to actually deform the magnetic field in the polar cap, then you find that the hydrostatic pressure in the column is high enough that neutrinos emission keeps the temperature well below the solidification temperature. So you're actually creating a solid lump around the polar cap as the star accretes. Okay? And then various of these nonlinear processes that are still very much under investigation by this collaboration would start to operate on this cap. And this is just the place you want energy to be released if you want to produce, say, a fast radio burst. So it's quite plausible that if indeed the core locks in the magnetic field over cosmological timescales, magnetars in old star clusters can be reactivated. They would also, of course, interacting with plasma acquired from another star, tend to be very strongly spun down as well. And you don't see spin modulation in spite of great efforts in repeating FRBs. Okay, so there are all sorts of potential applications for ancient magnetars, and this is an exciting direction. Then finally, and more broadly, Michael Kramer and his group likes to point out that there does seem to be some overlap in what's called the microstructure of radio emission in magnetars and in ordinary radio pulsars. In the sense, and there's a very simple relation between microstructure width and pulse period, which can be understood very simply as you have electrons and positrons created by some electromagnetic cascade with a Lorentz factor of about 100 streaming out. There is an emitting angle of about 10 to the minus 2 radians associated with very simple Lorentz aberration. And that then nicely defines this microstructure spin period relation. And the implication then is that the emitting plasma structures are yet narrower. Okay, so you have an upper bound on the width of these plasma structures, which, at my reading, has not yet been reproduced in any of the ab initio kinetic calculations of pulsar polar caps. So there are some things that are still missing in the understanding of current relaxation around both pulsars and magnetars, in my opinion. And we may then be in a great situation where being forced to consider such instability, say current of instabilities, in magnetars, we find that there may yet be some interesting benefits for more broadly for understanding rotation-powered objects. So that also is a direction that where bringing together different streams of research can be very fruitful. Okay, so that's it.